So I want to talk about some work we've been doing on active matter. I may first acknowledge the students who did the work, former graduate students, Sho Takatori and Wen Yan, both very excellent students who have now gone on to their independent scientific careers. And we had some support from the National Science Foundation for this. So let me first give you some idea what active matter, what I mean by active matter. So here's an example of macroscopic active things, birds and fish and penguins and even people. And so what is the distinguishing feature about an active matter system is such that the elements which are in this thing are able to self-propel. That's the thing I want you to get away from that. That's true both the macroscopic scale. It's also true on microscopic scale, these small microorganisms which can swim around and move. All of these are real experiments. Hard to see that one. This is the artist's conception of what a molecular motor might be doing inside your cell, but the rest are real experiments. And so what's the important thing to think about? I'm going to focus initially on just microscopic things. I want you to think about small swimming microorganisms, for example. And the feature that these things are able to self-propel, they convert chemical energy into mechanical motion and work. Okay? Each one has a little engine which allows it to move around, and they propel themselves. And we're going to talk about that. And I'm not going to focus at all on exactly how they do that conversion. I want to talk about the mechanics of how they move. After all, this is an IUTAM meeting where mechanics is in the title. So I'm going to focus exclusively on the mechanics of what goes on. So that's good. We won't need to know any biology or any chemistry. We're just going to do mechanics. Okay, so all be rest assured. And there's all kinds of microscopic organisms. I'll talk about these as well, which are synthetic particles which move in this very same fashion. So let me begin by just giving an outline. I want to talk first about the forces that govern the motion of these active systems. Then I want to introduce you to a new source of stress in active matter, which we call the swim pressure. And then just tell you some implications, applications of the swim pressure. And so let me first apologize to the few people in the audience who have heard me speak about this before. It might be all repeat for you. I think I might have a few new things in there for you. We've done lots of more things that I'm able to talk about in 40 minutes, and I'd be happy to talk to you about those things subsequently. But I think most people in the audience probably have not heard about this thing. So let's begin. And so here's a microorganism, which we might want to think about trying to think about how it moves in a fluid. And to me, when I look at that, it's just daunting to try to imagine how I could model or simulate or whatever else I think. It's even more daunting to imagine what's the biochemistry going on inside this organism, allowing it to change its shape and move its flagella and so on. But we can try to make some progress by realizing these are small. Typical things are sort of micron or so in size. They move typically about a body length per second. That's actually true for most living organisms, even humans. The fastest man is about a body length per second. As a result, they're in water, and so the Reynolds number for their motion is small. So we're going to talk about these microswimmers that swim at low Reynolds numbers. And one thing I want you to keep in mind is that it's always a two-phase system, by which I mean it's always the, the self-propelling body and the medium in which it's immersed. If you take this microorganism out in outer space, it cannot move. It has to push off against the medium, just like I have to push off the floor to be able to move. If you take me in outer space, I can't move either. So it's always a two-phase medium. Even though I won't really refer too much about the other medium, it's always present, and it's actually very important. Okay, so let's begin by microswimmers. And you probably hear the people refer to these things at small Reynolds numbers as force-free motion. And so what does it mean to be force-free? This seems like an obvious thing we should first ask ourselves. And so there's Newton's law of motion. Mass times acceleration is the sum of the forces. So if the force is equal to 0, then it's force-free motion by definition. But it also implies that any non-accelerating motion is by definition force-free. So when I came here on an airplane at 30,000 feet elevation, that was force-free motion. The thrust of the engines was balanced by the drag of the air. Okay? At low Reynolds number, so any non-accelerating motion is by definition force-free. At low Reynolds numbers, the inertia is not important, so all motion is force-free. So when someone tells you it's force-free motion, that's what that doesn't mean, because it's always force-free motion at small Reynolds numbers. What they meant to say was there's no external force causing the object to move. It's always a balance of a drag force and a propulsive force. Okay? That's the most important part of what goes on. And so now let's try to think about modeling some microswimmers. So the simplest one to think about is what's called a squirmer. And the biological example is a paramecium, which is more or less a body of fixed shape with small hairs oscillating on its surface, which it moves in beats and enable it to propel itself through the fluid. And from a mechanics perspective, that means that the fluid velocity satisfies It satisfies the translation rotation of the center of mass plus a local slip velocity associated with the small hairs on the surface of the body. Okay, that's how we're going to think about these microswimmers. It's at small Reynolds numbers, and so there's a linear relationship between the force, and I've gathered the force and torque together into one symbol, and the translation of and rotation of the center of mass in one symbol. That's the drag. And there's another term proportional to the slip velocity, how it moves its silly on its surface. These symbols are just hydrodynamic things, so you don't need to worry about them. That's my problem, not yours. All you need to worry about is the fact that there's a balance between a drag force and a propulsive swim force, but the net hydrodynamic force is 0. Okay? What else is next? Right. And it's a real force. That is, if you want to measure the swim force, you hold the body fixed, and that's the force required to hold the body fixed in space. You let the body go, and then it translates with the speed u. Okay, that's how things work. One thing that's important at low Reynolds numbers, as we heard about for force-free swimmers, as we heard about from Ganesh Subramanian yesterday, is the velocity of disturbance decays at least as fast as 1 upon r squared. Exactly how fast it decays depends upon the character of the body shape and the details of how it squirms, and so they can actually decay much more quickly than 1 upon r squared in certain circumstances. And I'm going to make life simple. I'm just going to think about this as a drag zeta times the velocity u. Okay? That's a squirmer. There's a simpler system. These synthetic particles, which are called Janus particles, they're first discovered by Paxton et al. They are, in this case, a small rod, a few microns in length, which is half gold and half platinum. You put it into water, and nothing happens. You throw some hydrogen peroxide in, and they swim. Okay? They move. There's nothing living, and there's no moving parts. Okay? Yet they swim and move around just like the microscopic living organisms. And the mechanism by which they swim is called self-diffusiophoresis. There is an asymmetry of chemical reactivity on one surface of the particle and not on the other surface. As a result of that reactivity, there's a flux of reactants on the concentration gradient. The corresponding flux of solvent backwards. That results in a slip velocity on the surface of this particle, and the mechanics of how it moves are identical to that of the paramecium. The mechanics of how it generates its slip velocity, its propulsive force is different, but the mechanics of its motion in the fluid is identical for the non-living one as it is for the living one. You can even make more complicated ones. You can make ones like these E. coli, and the mechanics is again the same. All that's changed are the hydrodynamic functions, are functions of the instantaneous body geometry, but it's still always a balance of drag force and propulsive force. Okay, so any complicated microorganism can always be thought about this way for these microswimmers. It's always the same. And that gives rise to the simplest model you can make, which is called the active Brownian particles. And that just, so here's my paramecium. It's a Langevin equation for its motion, no acceleration, just drag and propulsive swim force. And this is nothing more than what would be called an active colloid. In colloid science, we're used to having Brownian forces, interparticle forces, and shear forces. As a matter of fact, most talks you've heard about that talk about polymers and solutions and so on all use precisely this language to describe their behavior. They just don't have a swim force. So all you need to do is think all your colloid science stuff, but just add a propulsive force to the problem, and away you go. Okay? And we're going to make it life simple. We're going to have just the propulsive swim force and none of these other complicated forces from colloid science. So that's the mechanics of how these guys move. One thing you may have noticed is they tend not to go in a straight line. They undergo a random walk process. E. coli go under what's called a run and tumble motion, where they run for a while and change their orientation and then go off in a new direction. And the synthetic ones do the same thing. In this case, they change their orientation by rotary Brownian motion. As a result, they undergo a random walk and they diffuse. What's important to characterize that is there's a time scale, what's called the reorientation time, the time it takes before it changes its direction. And also, how big of a step does it take? That step L is called the run length or the persistence length. That's given by the product of the speed at which they swim and the reorientation time, tau r. As a result, they undergo a random walk, where the diffusivity is just the length squared divided by the reorientation time. And so there's a diffusivity associated with their swimming, which is u naught squared tau r. And it don't have to have all the same reorientation time or the same swim speed. There just needs to be a mean swim speed, a mean reorientation time, and central limit thermal hold, and they diffuse with a diffusivity which is due to their activity. It's not due to the thermal motion. Okay, so that's one most important thing I want you to realize is many active systems undergo this random diffusive motion associated with their swimming, not with any thermal energy kBT. Okay, so the next topic then is, from that, I'm going to derive for you a new source of stress in active systems. That's what we call the swim pressure. And so here's how the argument goes. So if you place a particle down in solution, it'll wander away by diffusion, because that's what it means to diffuse. So if you want to keep the number density n fixed, then you have to put it in a container. By virtue of the fact that you put it in a container, you now need to exert a force to hold the walls of the container fixed, or alternatively, the particle exerts a pressure. Just by the fact that you put it in the container, it generates a pressure. Okay? And so how are we supposed to understand where this pressure comes from? So what's the pressure? Now, here I have to admit to everybody, I've been teaching fluid mechanics for 30 plus years, and one day I woke up and I didn't know what the pressure was. And I was just like, oh, they're going to take away my license to teach, and that's so on, and that's just awful. So what's the pressure? This is true, was a true crisis, what the pressure was. So there were some pressures we know. There's the ideal gas law. The pressure is the number density times the thermal energy kBT. And you probably all did a calculation in undergraduate physics where you bounce the ball off the wall and calculate the momentum transfer to the wall and so on. But if you stop and think about it for a moment, it's not important that they hit the wall or my shirt or the ceiling or the floor. It's just the fact the particle can't get out of the room. It's just a random confinement pressure. That's the number density times thermal energy kBT. One more relevant to us is what's called the osmotic pressure of Brownian particles or molecular solutes. In this case, the fluid is able to escape the box, but the particle isn't. And there's an osmotic pressure, which is the same thing as the number density times the thermal energy kBT. Okay? And these are really just the result of the randomness associated with the process going on. And I'm going to convert that Brownian osmotic pressure into a different form because I can write it as the number density, the drag, and the diffusion coefficient, because we know from Stokes-Einstein-Sutherland the diffusivity is the thermal energy divided by the drag. I think this is actually a better way to think about the pressure. It's really the random walkus of the particle. It just happened to be kBT. It's really the diffusion of the particle which generates this random isotropic pressure in the system. Well, I told you before that our active particles also have a diffusivity, a swim diffusivity, so they generate a swim associated with that, which is nothing more than the number density of the drag and the swim diffusivity. I've now written that down in terms of what it is for a swimmer. It's u naught squared tau r divided by 6 in 3 dimensions. And analogous to kBT, I can define the KSTS, which is my definition of the activity of the particles. So they generate this pressure just from their random walk motion. For those that like mechanics, since this is a mechanics conference, there's also a fundamental definition of stress. This stress is minus the number density, drag, the diffusion coefficient. The micromechanical definition is a moment of the force. The force is the swim force, which is the drag times the swimming speed. And importantly, the moment arm is not the body size, but it's its run length or its step size, L. Okay? And that's give you a micromechanical formula. Even more micromechanically, what happens is the particle comes up to the semi-permeable membrane. It can't move now. It stops. It pushes. It's still swimming. Pushes the swim force until it turns and run away. And that's how it mechanically transmits its swim force to the boundary to generate its pressure. So that was the derivation of the pressure. So we thought, let's go see if that's true or not. So the first thing we tried to do was some computer simulations to measure it in simulation. And so we put a bunch of particles in a box. The dynamics are very simple. There's drag. There's a swim force. The swim force is this drag times the swim speed in some direction q. That direction of motion just randomly reorients with a time scale tau r. Since it's a finite concentration, we need to worry about whether they might run into each other. So we simply had a hard sphere repulsive between the particles. And there we go. This is the result of the pressure appropriately normalized as a function of volume concentration. And you see it all along this straight line we have here. There's a number of different colors and different symbols and so on. So let me explain those to you. There's one very important parameter which is going to come up, which is we call reorientation Peclet number. It's actually the ratio of the body size A to the run length u naught tau r. It's called a Peclet number because it's swimming advection over diffusion, but a diffusivity is a swim diffusivity. So it's a funny Peclet number with a velocity in the denominator. People are very upset with me for having defined this that way, but that's what it is. Just think of it as a body size compared to the run or persistence length. And you see, we varied this by several orders of magnitude. It didn't make any difference. We also did calculations two ways. One where we had actual physical walls and calculated the force transmitted upon collision with the wall. One where we had periodic boundary conditions and used this statistical mechanical definition of the stress. They all agree, and they all lie along the ideal gas line for the swim pressure we have. And there's no thermal energy at all. Purely active. Okay? So the next thing we thought we'd try to do is, could we measure that in an experiment? And so my student, Sho Takatori, went over to visit Jan Vermont in Zurich to try to do these experiments. We first made Janus particles, which are, in this case, they're polystyrene particles, roughly 2 microns in diameter, coated with platinum. And they swim, as you see, swimming around here. These particles happen to be light, so they actually float at the air-water interface. There's a large supply of hydrogen peroxide in the water beneath it, so it keeps supplying fuel for it, so they can swim for a long time before they exhaust all the fuel. And they run around, and they have the same mechanism of self-diffusiophoresis or self-electrophoresis. And so the experiment that Sho did was he put them, here's the particles, and we put them in a trap. So there's the trap. The trap is actually an acoustic trap. So it's like an optical trap except with sound waves instead. And so you trap the particles inside this trap so we can watch them wander around. They have both a Brownian diffusion coefficient because they're micron-sized particles, as well as a swim diffusivity. In this particular experiment, the Brownian diffusivity is 0.1 micron squared per second, where the swim diffusivity is 100 microns squared per second. They're 1,000 times more active than they are Brownian. Okay? And as you can see with the little circle, we'll come up here again, we can then track the particle motion and just build up a histogram for what is the there we go, build up a histogram. Oh, before we build the histogram, we can make the trap of any radius. We can actually make the trap a harmonic trap as well. So we put the particles in a nice harmonic well, and we can watch where they go and build up a histogram to ask what's the probability density for finding a particle relative to the center of the trap. This is what we found as a function of the distance from the center normalized by the persistence length. The red symbols are experiment, the blue are simulation, and the black is the theory. And the theory is nothing more than the Boltzmann distribution, but not with KBT, but with the activity KSTS instead. Okay? So that gives rise to what we call rule number 1 of active matter. Whenever the length, in this case the trap size, is large compared to the run of the persistence length, everywhere you find KBT, you get to replace it with KBT plus KSTS. You can't tell whether the motion was Brownian or active. Okay? Then we wanted to try to measure the swim pressure, and we found something that we weren't anticipating. This shows the pressure in an experiment as a function of time. Again, the red are experiments, the blue simulation, the black is the theory. The theoretical prediction is the following. First of all, there's a factor of 2 because we're in 2 dimensions as opposed to 3. We find the pressure is not equal to 1. It's reduced by a factor alpha, and that factor is nothing more than the ratio of the run length to the size of the trap. So what it's telling us is if you bring the walls of the container in closer and closer, comparable to the run length, the pressure goes down. Okay? That's the most important thing I want you to remember. That's rule number 2 of active matter. Whenever the length is comparable to the run length, the swim pressure goes down. And the reason for that is that you've cut off the large steps the particle could have taken if it had more room to run around, and that reduces its diffusivity and reduces its pressure. That's a phenomenon which is well known. It's called the Casimir Effect. I don't know any quantum mechanics, but I can read Wikipedia. And so what the Casimir Effect is, you put 2 parallel plates. The vacuum fluctuations are unbiased outside, but they're restricted between the 2 parallel plates. That results in an attractive force between those 2 parallel plates. As in all good things, there is always a fluid mechanical analog to everything. So there's some experiments in a fluid where you put 2 parallel plates in a tank of water. You start the tank vibrating, and the plates come together because the surface fluctuations are unbounded outside the plates, but they're restricted between the plates. There's an attractive force that results in them coming together. You can also argue for those that colloid depletion flocculation. You can argue this in the same way. It's just cutting off the spectrum of fluctuations reduces the pressure. That's been known for people who have boats in harbors. That's why the boats have bumpers on the sides, because the fluctuations out on the channel push them together. So it's been known since antiquity this happens. We can do a simple theory to calculate that, and don't worry about the details. Just worry about the fact that we can then calculate what the pressure is where the spacing between 2 plates is comparable to the run of persistence length. The details aren't important. What I want you just to get about from the fact is the fact that you see that once even the spacing of just twice the run length, you've dropped the pressure significantly down by a factor of 2 or so. Okay? Because I cut off the spectrum of fluctuations available to the random walker, its diffusivity goes down, its pressure goes down. You might have thought I was clever with a Casimir effect. I wasn't clever at all. There's a paper which is entitled Casimir Effect in Active Matter Systems by Ray, Reichert, and Reichert. And what they did was some simulations of parallel plates and random active particles and measured the attractive force. If you can see here, it's kind of hard, as a function of the ratio of the separation to the persistence length. And this is what they found. That's the correlation that they found from their simulations. And from our simple theory, you can actually predict analytically exactly what that is, how exactly it scales with the spacing to the run length. We predict a coefficient of 1 over the square root of 2. They had 1. They must have made a mistake. No. So that's what happens. Okay? So the most important thing I want you to remember is the following. There's a diffusion or random or entropic stress. The stress is minus the number density, the diffusivity, the drag coefficient, and the diffusion coefficient. This is a single particle result. It applies to Brownian motion. It applies to E. coli. It applies to Janus particles. It applies to molecular motors running along microtubules that exert a tension on the tube just because they're doing a random walk along that tube. Okay? It actually applies to things like fish. I don't have time to tell you about it, but we can actually add the inertia back in, and the result is unchanged from what it was in the absence of inertia. The exact same formula, even with inertia of the body that moves. One back thing I want to go back. Sorry, no, go too fast. Go backwards. Go backwards. There we go. Back to this aspect of confinement. The particles are confined in this direction, but they're unconfined in that direction, which means that the stress along the axes is unchanged, unconfined, whereas the stress perpendicular is confined and different. That means just by bringing the walls in, you've generated a material which has an anisotropic stress. Stress this way is different than the stress that way. Mechanically, that's perfectly fine as long as the boundaries are commensurate with the principal axes of the stress, as they are here. But if you just tilt the walls, then it has to flow. I can't tell you how fast it flows, but it just has to flow. Okay? Just from that argument alone. One other thing about this to illustrate the fact that, that this formula is true is we try to think about what happens in a shear flow. You put one of these swimmers in a shear flow. Now, there's a coupling between the fact that it has a finite time it runs around and explores the velocity gradient field available to it. The diffusion in the flow direction is different than the diffusion in the vorticity direction than it is in the velocity gradient direction than the vorticity direction. But there's also diffusivity along the xy axis. Particles are diffusing out and pushing out, as I illustrate by this little cartoon, on the xy axis in the same fashion that a pusher particle exerts extensile stress on the axis. Diffusivity is positive, the stress is negative. That means it's acting in the same direction. I'm trying to move the boundaries. That means from a point of view of what the viscosity is, the viscosity has gone down. And so this shows you some experiments which are done by Lopez et al. The effective viscosity of E. coli in a Colette device compared to the solvent viscosity. You increase the concentration of the swimmers, and the viscosity is reduced below that of the solvent water. What's important is the Peclet number, which is now shear rate times the reorientation time. At high Peclet numbers, particles just tumble, and so there's no effect. You go back to the viscosity of the solvent. But as you add particles, you actually reduce the viscosity, and you can reduce the viscosity down to 0 to generate a superfluid, so-called. Okay? And these lines just show you, if you take this simple theory, this theory has in it both the swim stress as well as the hydrodynamic stress associated with stresslet pusher particles. We have a prediction for what happens. Okay. And the last thing I want to remind you, in fact, this is just a single particle result. You can add the inertia, and the body size doesn't enter. Okay? It's independent of size of the object that swims. And so the last thing I want to leave you then with, another application of this is some aspect for phase separation. So it's well known that we see a flocks of birds and schools of fish, but also, it's hard to see this, guys, microscopic things also tend to do this kind of clustering phenomena. And so I want to see if we can't describe something of that. And we're going to have just that notion of the swim stress is going to help us figure out what happens in this system. So let me show you some results of a simulation. On the left-hand side are, first these are 40% by area. There are 5,000 particles, the periodic boundary conditions, in 2 dimensions. They're disks. On the left-hand side are particles which are undergoing purely Brownian motion. The right-hand side are particles which are just active, no Brownian motion at all. And I will see what happens. So you see the Brownian system on the left. It stays in a random dispersed state because at this particular volume concentration, the hard disk problem is just a fluid, whereas the active system doesn't. They just don't. They have clusters of particles together very densely with some dilute gas-like particles between them. That happens in the computer. It also happens in experiment. These are the original experiments by the group in Lyon, which have, if you will, small clusters of particles with gaseous-like particles around them, as well as, those are hard to see, the colloidal surfers by the NYU group, which have little crystallites, you can see here, with some gaseous particles running around them. So the question is, why does this happen? You start off with particles which are just repel each other if they run over each other, and they swim and reorient, nothing else, and they spontaneously form clumps. So what's going on? It sort of looks like equilibrium gas-liquid coexistence in some sense, except these are purely repulsive particles. To get a liquid, you need to have attraction between particles. Here they're just repulsive, yet it forms this thing. So, and my explanation for that is going to be the swim stress is going to come to the rescue to help us understand how this comes about. So here it goes. So at low concentration, here's my particles running around. I'm going to say the pressure is high. It's high in the sense that the particles can take all their steps as far as they want to go and have their full swim steps and have the full swim pressure associated with that. But as I increase the concentration now, let's imagine that little box of particles there, now I'm being restricted in my swimming by running into my neighbor. So rather than being confined by the walls, I'm confined by my neighbors. And as a result, the diffusivity is low, the pressure is low because rule number 2 is active. Now the confinement comes not from the boundaries, but comes from running into one of my neighbors, and that confines my pressure. So to see that, I'll show you results from simulations here. This is the pressure normalized appropriately as a function of volume concentration. What I showed you before was this little red box down here. Now I'm showing the rest of the result for all high concentrations. It's a very busy plot. So let me begin with going up along the diagonal, which is the ideal gas line. And first start off with a particle, these symbols in stars. Now the reorientation Peclet number does matter quite a lot. The reorientation Peclet number of 100, that means the steps are very tiny compared to the body size. Take a step, reorient. You follow along the ideal gas line until you reach the maximum density till you run into your neighbors. As a matter of fact, in the limit the step size goes to 0, the mechanics are identical to Brownian motion. That's what Brownian motion is. Except this case is due to activity. They're swimming instead, but the mechanics are identical, and you'd be along the ideal gas line except with KSTS instead of KBT. But as you increase the persistence, I start to run into my neighbors, they constrain me, and my pressure then starts to decrease, and once I've reached even a reorientation Peclet number of 1, I've almost reached the limit of even smaller reorientation Peclet numbers. They all collapse down to the same curve in which we're confined. So that was rule number 1 when I'm very dilute, and rule number 2 makes me confined, and the pressure goes to 0 at random close packing. Okay? So now you have a pressure, which is a decreasing function of concentration. That's trouble. That's mechanically unstable. A fluctuation occurs, particles come in, pressure goes down, more particles come in, and it runs away. Okay? So that's mechanically unstable. There is a stabilizing effect, however, because that's not the total pressure in the system. That's just the single particle swim pressure. There's also the usual pressure you have of a collisional pressure between particles, the kind that we're most often used to thinking about. And this shows you this collisional pressure appropriately normalized as a function of volume concentration. The collisional pressure, that's the formula for it, again from hard sphere collisions. The force is still proportional to the swim force, activity, zeta u naught, but importantly, there are 2 things important. One, it takes 2 particles to generate this stress, as opposed to 1 particle for the swim stress. And furthermore, this stress is transmitted upon contact, so it scales with the particle size, not with the relative persistence length. As a result, the ratio of the collisional pressure to the swim pressure is very small, particularly at small reorientation Peckley numbers, except at very high concentrations where there are lots of collisions and that pressure runs up high. For those that know fluid mechanics, there's also a fluid mechanical pressure or stress as well. That's a single particle result, but that's set by the body size, not by its run length, and that's not important at the small reorientation Peckley numbers where all the interesting things happen. Okay, so now we have one pressure which goes down, one that goes up. So the total pressure, which we call the active pressure, as a function of the normalized by the appropriately normalized as a function of the volume concentration. This is what the active pressure looks like as I vary the reorientation Peckley number. Start off here at black, which is relatively high. And now on this, I'm going to superimpose the Carnahan-Starling equation of state for hard spheres. It's identical. You can't tell the difference if we're Brownian or if they're active. But as you decrease the reorientation Peckley number, it's like decreasing the temperature. You eventually get down below here where you have a van der Waals loop. You have a coexistence between a dilute region and a dense region. Actually, it's between a gas and a solid, for those that really want to know about it. And if you look at any thermodynamic textbook, you'll find a pressure-volume diagram with isotherms along there. In this case, it's a volume fraction as opposed to volume, so I'll flip that around for you. So it looks just like you look from a thermodynamic system, except there's no thermodynamics here at all. This is just mechanics. Okay? Nonetheless, you get this kind of behavior. And we can even go further than that. We can actually work on an equation of state. That is, I can figure out what the active pressure is as a function of the volume concentration and the reorientation Peckley number, which is like the temperature of the system. So I'm going to make a very simple model for the active pressure. There are two pieces, the swim pressure and the collisional pressure. The swim pressure goes down, and we actually know how it goes down. We can work out analytically in the limit of persistent swimmers that it goes down like 1 over 1 plus phi times the pair distribution function at contact. That's just, you can do a microreology problem and figure that out. For the collisional pressure, now here I'm going to make an argument that may not be true, but I'll make it anyway. So if you think about the hard spheres, whether they're molecular atomic hard spheres or Brownian hard spheres, the volume fraction dependence of the pressure is always the same. So I'm going to argue it's the same for these active particles, except they're driven by activity instead of driven by thermal motion. And as a result, this is then going to be the appropriate normalized collisional pressure, which is again the pair distribution function of contact times the volume fraction. Now I don't know what the pair distribution function of contact is. I'm just going to take the hard sphere Carnahan-Starling equation of state. Just borrow it over. And now I have a closed prediction for what happens. And this shows you then this nice colorful PVT diagram where the pressure is in color, volume fraction on the bottom axis, and these correspond to different isotherms, if you will, and the reorientation Peckley number at the left-hand side. So this system has a spinodal, which is defined mechanically where the variation of pressure with volume fraction is negative. It's got a critical point. It's defined by the first two derivatives of the pressure with respect to volume fraction are 0. Now, most people think of those things in terms of free energy, but there's perfectly mechanical things. You don't need to know any free energy at all in terms of mechanical stability. So it has a spinodal, it has a critical point. And let me just show you a comparison of some other simulations which were done by Wysocki et al. A few years ago, where the solid symbols they reported a two-phase region, the open symbols reported a single-phase region, and that shows you a comparison between that simple theory, which has no adjustable parameters in it, and the results of those computer simulations. Okay, so I'm almost with the end, and so let me just leave you with a few other nice things. Let me just show you these are just fun things now. So back to these trapped Janus particles at the interface. I'm going to show you now a case where we made the trap very, very strong, and then we turned it off. Okay, so I want you to just watch what happens. So the trap is very strong, and then at a certain time we're just going to turn the trap off, and you'll see what happens. it explodes. Okay, well, I call my supernova of active matter. Okay, got to compete with the astronomers at Caltech. And the reason that releases the swim pressure. That's not how a Brownian system would melt if you release the confinement. It would not behave that way at all. If you have good eyes, if you watch the next blast take place, you'll actually see there's a shock wave in concentration sent out that actually goes off ballistically, and we actually have a theory to describe this in the wave propagation for these kind of systems. It actually explodes in that sense. And then I'll leave you with a few more minutes, a few other things. We're having fun playing with mixtures. So this is a mixture of active and passive. The red particles are active. The white are passive Brownian particles. Total area fraction is 70%, and they're 5% active. And they're rather persistent, with their activity compared to thermal energy is 3,000 roughly. Don't ask me why it's 3,750, but it is. And what I want you to show you, if you watch here in the middle, is that the active particles will sort of gather up the passive particles into a big ball. Okay, sort of like sheepdogs herding the sheep, gather them together like this. And actually can then drive it over the phase boundary for the hard disks, and you'll see these guys will crystallize in the center here because they're pushed together by the active particles. And you can turn the activity on and off by light and other means. You can actually then drive the morphology and create microstructures by just having a sprinkling in a few active particles into the system, and actually now obtain different microstructures in different states that you might not be able to access another way. And this one I just like because it's just wild. So this is area fraction of 50%, 1% active particles, but they're really active, and the red guys. And watch what they do. So I don't know what this is, whether it's an ant colony or a biofilm, or it's just active particles. Just running around, pushing stuff around, making funny things. No theory for that, but I thought it's just entertaining. So with that, you can stare at that all day. It's sort of mesmerizing. So trying to figure out what's going on. So I'll stop that and just say, all I want you to remember that all that's important is randomness and dissipation, and you get a swim stress. Thank you very much.
Hey, John, lovely
Yes.
talk. No distinction appeared between the pushers and pullers in what you were doing.
Correct.
So what would be needed for that distinction to show up, which has consequences for stability under shear, for example?
So this is an additional stress. There also are hydrodynamic stresses as well, which I did not include. And there the pusher-puller makes a distinction. These are always like pushers. So we actually predict that due to this mechanism, even pullers under the right conditions would display the same instabilities. That's yet to be experimentally tested. Oh yeah, yeah. It's got nothing to do with the mechanics of how it moves don't matter. Okay. Yes, Ganesh.
What about if I'm sitting in the fluid, the hydrodynamic signature via the fluid motion caused by, if I have a suspension of Brownian particles with KT, and a suspension of active spheres with KSTS being equal to KT.
Mm-hmm.
And if I sit in the fluid and start sensing the fluid motion in an unbounded suspension of these things, a system, two systems with the active and passive temperatures being identical.
So what's the question?
Will there be a difference? So you're saying that it's the essence of your talk is we can think of them the same way, right? Provided
That's right.
So now, if I'm sitting in the fluid, can I still think of them the same way, or will I feel a difference?
It depends. So if a particle moves one way, an equal volume of fluid has to move the other way, and so that's just going to be slave to the motion of what the particles do. So in the active case, you would still see fluctuations in the fluid the same way you'd see fluctuations of the active particles. The tracer diffusivity of the fluid would be matched to that of the active particles under certain conditions. Other conditions, it's not.
More generally, John, you can speak of a swimmer stress instead of just pressure.
Right.
Yeah.
I said the stress, right.
The question is whether dissipation it may be essential in the fluid mechanics domain, but over in solid mechanics, you have elastic stresses that are built in, residual stresses that are the result of active processes. So I think there's, the question is at the continuum level, if I think about modeling swimmers or these systems with residual stresses in solids, I think the idea is you have, you didn't write down any continuum momentum balance or anything like that.
I did not.
So you still have no sources of momentum, no forces.
No
but
forces.
You have self-equilibrated stress fields
Yeah.
that are involved in that have divergence of stress equal to zero.
Yeah.
So your, I'd say your swim pressure is in some sense a self-equilibrated.
I don't know what you mean by that, but these are just simply active particles. The distinction between dead matter is these guys have their own internal engine. They get to run around and move around by themselves, and that imparts to these are just a single individual particle. So in the context of any kind of condensed matter, there are all these interactions. This is just a single guy by himself generates this pressure and stress.
Yeah,
so it's very different.
You've got entropic elasticity, but in solid mechanics you don't need that. You've got other kinds of elasticity.
But you have no active processes.
Pardon?
You have no active processes in the sense of, and
No,
in the sense that there's an internal engine within inside each particle.
oh yeah. You, in the growth process, when cells grow.
Sure, cells are living. Cells are living.
You
This,
violate the mass balance.
cells are living, so cells display the same pressure.
Yeah.
They do. This is where it comes from. Yep.
So you showed one of the rheological experiments where people have looked into the rheology of the bacterial suspensions, and there they observed the reduction in viscosity. The bacteria, the non-isotropic active particles, right?
That's
so what
right.
can we expect if the particles are isotropic? Should we still expect a reduction in viscosity?
I say yes, because the swim stress doesn't care what your body shape is. This is a prediction. Okay, it could be wrong. So please go try to prove me wrong.
Because they argued that the bacteria, due to their anisotropic shape, they align along the stress
Well, this thing
direction.
diffuses along that direction, right?
Right.
So it has the same element. It still has diffusion, preferential diffusion along the extensional axis of the flow, and it's pushing out just like a pusher does. So that's where it comes from, but it's from a different source of motion, just due to the coupling between the random walk and the convective flow.
All right, thanks. Jim?
John,
Yeah.
is there any significance to gradients of swim pressure?
Yes,
Do they drive motions of the
Yes.
fluid, for example?
yes. You can. I didn't do it, but you. I talked about the level mechanics. We have a thermodynamic level as well. I didn't mention thermodynamics. We have a thermodynamics. We also have a continuum mechanics in between. Yep.
Hi, John.
Yes.
I had a similar question. If you have now a gradient in your active temperature, in your TS, is there something that's the equivalent of heat and Fick's law? Is there? I mean, are you heading towards?
I didn't think about it going to a fixed law. KST. So if you change activity, so there are. Let me show you. I'll find an experiment by someone and shows you what happens if you can vary activity. So bear with me 1 second. This is much better than me telling you anything to show you some result. If I can find it. Okay, so Roberto Di Leonardo in Rome has made particles which, bacteria, which are light sensitive, so he can turn on or off their activity, and by changing the light pattern, he can convert Darwin into Leonardo, Albert Einstein, there we go, and make the Mona Lisa as well. So that's spatially varying and modulating the activity of the bacteria. You can paint with them.
That's active.
That's more fun than gradient diffusion, right? You can do so. You can paint with them.
That's Brady's active Fick's law.
So you can do lots of things. So there are lots of things you do, having variation of activity, both temporally as well as spatially. You can pattern things, you can move things, you can do all kinds of stuff that way. And you can do those, in principle, with synthetic particles as well. So it opens up a whole window of how to think about controlling microstructured materials with active particles. Question over there? Yeah.
So if you have the osmotic pressure, that's the chemical potential of the solvent.
Yeah.
So with the swim pressure, does that affect the chemical potential of the solvent? If you have that?
Well, so the fluid, in this case, the particles in the fluid, they're incompressible. So you have to think about the chemical potential in an incompressible medium, and the osmotic pressure is related to chemical potential of the particles. So there is the analog of that associated with the active pressure. You can define an active chemical potential. I didn't talk about that. Then you can define a binodal for this system as well. Whether that's true or not is a big question, but you can. I made all those definitions. Have a wonderful paper that's called Towards the Thermodynamics of Active Matter, where we do all those things and have a Gibbs free energy, and away you go.
Okay, I think we've run out of time for questions, so please join me in thanking John for a great talk.